So today we are going to have a presentation on ferrous fines charging rules in blast furnace operation. The scientific logic behind three critical documented operating rules that every blast furnace operator must understand. These rules govern how we manage ferrous fines particular under 5 mm and control coke quality to maintain a stable furnace operation. We'll analyze the physics, the chemistry, and the practical plant experience that validate these rules globally. By the end, you will understand not just what these rules are, but why they exist from the first principle. So let's begin with the further slides. The three rules we are examining today work together as an integrated system to maintain blast furnace stability. Coming to the rule number one, total fines plus low grade ore must not exceed 8% of the ferrous burden. This rule preserves permeability. Now coming to the rule 2, which is about the M10 value. The percentage of coke below 10 mm after mechanical testing must remain below 5.8%. So these prevent excessive fines generation inside the furnace. Coming to rule 3, the harmonic mean size of the coke must be at least 42 millimeters. This ensure we maintain proper gas distribution and control thermal behavior. These three rules are not independent recommendation. They are tightly linked through the fundamental physics of burden permeability and gas flow dynamics. Violate one and the other become difficult to maintain. So now coming to the rules one by one, and now we can say that let's start with the rule 1, the 8% total fines limit. Why is this critical? When we charge ferrous fines, particles smaller than 5 millimeter, they fill the interstitial spaces between large ore and coke particles. Think of fines as sand filling the gaps between rocks. As fines accumulate, they systematically reduce the void fraction, the percentage of empty space through which the blast gas must flow. This reduction is exponential and dramatic. The result is catastrophic. Gas pressure increases exponentially, creating a pressure resistance that can spike to 25% or more in just hours. This leads to a ring formation where material segregate and block the entire cross section. Escape formation on the lining and unstable furnace operation. The eighth threshold is empirically proven across global steel plants as the maximum sustainable level. Now coming to the now let's look at the mathematics behind the permeability control. The Kármán Kozin equation describe how fluid flow through a porous media. Now, as for the permeability, our K equals d square times the epsilon cube divided by S times 1 minus epsilon squared, where d is particle size, epsilon is void fraction, and S is surface area. Here the critical insight, permeability depends on the particle size squared. This is quadratic dependence. What does this mean practically? If you half the average particle size in your burden by 75%, size in your burden by adding more fines, you reduce permeability by 75%. That's not linear, it is diversity. The 8% threshold exists because beyond this point, void fraction collapse dominate. You cannot maintain adequate gas flow. Plant validation confirmed that exceeding 8% fines causes wind pressure increase exceedingly 25% within hours. So this is not theory; it's measured a reality from the operating furnaces data and statistics. So impact. So what happens when we violate the 8% fines limit? The consequences ripple through the furnace dynamics. First, Borden descent slow dramatically, increase gas pressure, create a resistance that literally prevent material from falling at normal speed. Material bridges form stable arches that block flow. Your descent rate can drop from normal 100 meter per day to 40 to 50 meters per day. Second, thermal maldistribution emerges. Gas preferentially flow through zones of highest permeability, especially the furnace periphery. The central core stay cold. This creates a radical temperature gradient instead of uniform heat distribution. Third is the ring formation, which we have already discussed. At temperature around 800 to 900 degrees Celsius, coke sinter with ore in the segregated region, creating a hard ring that block the entire cross section. And this is an operational emergency. And fourth is the escape risk. The cold spots allow slag to adhere and build on the refractory lining, ultimately threatening furnace integrity. This is why the 8% rule is non-negotiable. Now coming to rule number 2 details, and rule 2 addresses the source of problem, coke itself. MICOM 10 stand for mass percentage of coke below 10 millimeters after ISO 9006 drum testing. This test simulate the mechanical aberration your coke experiences as it descends through the furnace over 6 to 8 hours. Why the 5.8% threshold? Here the logic, if coke degrades into less than 6% fines under typical in furnace stress, and your ore contribution to fine is around 2 to 3%, then your total fines approach the safe 8% limit. In other words, MICOM 10 less or equal to 5.8% ensure that even under severe mechanical and thermal stress inside the furnace, the coke doesn't become a major fines generator. These thresholds reflect an optimal balance. Coke must be strong enough to resist breakdown, but the strength specification must be achievable and economically reasonable for coke procedures. Now, coming a more focus on the coke breakdowns. Uh, what causes coke to break down inside the furnace? Three primary mechanisms. First is thermal stress. Coke experience temperature cycling from the ambient to 1500 degree Celsius as it descends. This creates 10 to 15% volumetric changes. The material expand and contract repeatedly, initiating microcrack. What is the second reason? Second reason is the mechanical impact. The body descent approximately 100 meter per day. Now particle cascade and collide. This particle to particle collision crush weak surface area, fragmenting coke into smaller pieces. And what is the third? Third is the chemical attack. So carbon dioxide and water vapor gasify coke chemically. Weak pores enlarge gradually, creating a stress concentration point that lead to fracture. The 5.8% MICOM 10 specification quantifies an acceptable degradation rate. Testing shows that coke with a MICOM 10 coke with a MICOM 10 is MICOM 10 coke with a MICOM 10 of 5.8% generate approximately zero point 0.5 to zero point 0.7 kilogram of fines per ton of coke charge. Combined with ore fines, this keep total fines within the safe 8% window. High MICOM 10 coke say 6.5% or higher amplify total fines beyond 8%, triggering the cascade of problem we discussed earlier. Now coming to our next slide, which says that why do good coke have low MICOM 10? The answer lies in microstructure. First, carbonization maturity. Good coke have a volatile matter below 0.5% and fixed carbon above 88%. This indicates complete coal transformation into a dense rigid carbon matrix. Less mature coke with a residual volatile content is mechanically weaker. Second is the pore structure. Optimal coke has 40 to 45% porosity, but critically those pores must be in the zero point 0.5 to 2 micrometer range. A small pore resists crack propagation. Large pore become fracture initiation sites. And third is the coke density. Coke exceed 1350 kilogram per cubic meter correlate with low M10. Density indicate excellent coal coking ability and structural integrity. Plant reality, what is that? The high M10 coke spiral operators towards failure. They amplify total fines beyond 8%, triggering ring and scab formation. Eventually, you are forced to reduce coke quality further just to maintain a decent rate, a safe defeating a spiral. Good coke quality is the foundation of a stable furnace operation. So now coming to our rule 3, why HMS should more or equal to 42%. So rule 3 addresses coke size distribution, but this rule uses a specific metric, harmonic mean size or HMS. HMS definition, what is HMS? It is a weighted average coke size that account for the shape of your size distribution. Importantly, it emphasizes coarse fraction. Large coke pieces receive disappropriate disappropriate weight in the calculation. Why use harmonic mean inside of a simple arithmetic mean? Because what matters most for permeability is your coarse fraction. If you have one giant coke piece and thousand of teeny fines, the giant piece occupy a small percentage by count but control word structure. Harmonic mean captures this correctly. The 42 threshold empirically, when HMS drop below 42 millimeter, your distribution contain more than 15% ultra fine coke particle below 3 millimeter. This causes void collapse and catastrophic permeability loss. The 42 millimeter specification is validated across global plant regardless of ore layer, limestone composition or coke origin. It is a true universal rule grounded in the physics. Now coming to the HMS, why does HMS matter so much? It control one of the most dangerous phenomena in blast furnace operation, gas channeling. When HMS exceed 42 millimeter, you maintain a adequate coarse fraction. This preserve large void channel for uniform gas distribution. Gas flow relatively evenly throughout the burden. When HMS falls below 42 millimeter, fines accumulate preferentially in the furnace center. Gas find the path of least resistance and segregates preferentially flowing through the peripheral raceway. Raceway zones. The central core experiences gas starvation and thermal maldistribution. This is catastrophic because it violates thermodynamic balance. Uniform reaction front depends on the uniform gas distribution. Plant data confirm when HMS decline from 45 millimeter to 38 millimeter, scab formation typically preceded by a 5 to 7 days. The early warning sign and signals are there. Operators who monitor HMS can intervene before failure. They maintain HMS below 42 millimeter. You maintain heat flux uniformly and prevent the gas segregation that lead to ring and scab. Now coming to, so let's in this slide let's look at the mathematics of void fraction and size distribution. Void fraction epsilon equals 1 minus the ratio of bulk density to particle density. It's a fundamental to permeability. Here is the critical discovery: narrow coarse size distribution, high HMS, maximize void fraction. Broad distribution with fine particle minimizes void fraction. A practical example, coke with HMS of 50 mm achieve approximately 45% void fraction. The same furnace, same condition, but coke with HMS of 35 mm contain more fines, yield only 38% void fraction. That's a 7% point absolute loss in the voidage. In a 4,000 4,000 cubic meter of furnace, this represents catastrophic permeability collapse. The quality correlation is that the good micum 10 coke maintain HMS above 42 mm even after descending 50% through the furnace. They resist degradation. High micum 10 coke shed fines continuously, driving HMS downward towards the failure. This is why rule 2 and 3 are inseparable. Good coke quality maintain size distribution stability. So how do all three rules integrate into unified framework? Through heat flux measurement. Heat flux is measured in a walls per square meter through the furnace lining cooling steps. It quantifies thermal power transfer and reflect material temperature distribution inside. Why heat flux measure stability? Uneven thermal distribution create localized hotspot. Hotspot mean high local heat flux. Normal stable furnace shows heat flux of some optimum value per square meter, which is again exclusively different for different size and design of furnaces. Now, excessive fines and ring formation produce localized peak of maybe 150 to 200 watt per square meter. Now, connection to our three rules, excessive fines beyond 8% cause ring and channels thermal maldistribution, elevated heat flux. Micum 10 coke generate excess fines, same thermal signature. Low HMS cause gas segregation, thermal imbalance, and peak heat flux. So, predictive power is that the heat flux trending reveals rules uh, uh, rules are getting followed or not. That means whenever the flux has got a lot of deviation, that means your the coke sizes, the micum values, and the fines load all are getting attacked together. Now, here is how operators integrate all three rules into daily decision making. I call this the monitor and respond protocol. So, in this we can see that heat flux is deviating on a higher side. Immediately we have to check the fines percentage, micum 10 and HMS. So, whenever our flux indicates, we must have to see all these aspects which were earlier discussed. Anticipating that a ring risk, what we said, that fines loading create a that shade of impermeable ring. So this is a furnace emergency requiring active intervention. Mm, So we can say that once we have got a flux deviation to a higher extent, then we must have to attack all these together. It is not that one by one only we have to see. So this what is being shown, all different colors. So we have to see the heat flux if more than 140, then we have to check the fines, we have to check the micum 10 values, and also we have to check the harmonic mean size immediately. So all three factors, as we have already discussed, uh, we have to act together. Now, you might ask, are these rules specific to furnaces? To Indian conditions, we can say the answer is absolutely no. These rules are universal and they are not very specific wherever you are there. you can apply these rules. That threshold value, as we have already discussed, is 8%. So if your burden share and fine share is the inferior burden and fine share is 8% or more than that, then you must have to focus on all these area, whether you have got a deviation of flux. Is operators start monitoring what is the best line when the furnace was doing well, and now once this fines loading is increases, whether flux is showing that type of reflection or not. If flux is showing the reflection, then you must have to check their micum value and granulometry together, and you see that this work very well. So this has been applied to many of the furnaces, and we found this all three rules are working very well. So this is one good way to analyze the things and act quickly in the any abnormal situation in the furnace.